Hello, my name's Simon Hickman and I'm one of the directors of Multipix Imaging. Today I would like to talk to you about anomaly detection. The purpose of this presentation is really to get across the concept of anomaly detection and a little bit about what's behind it, but really only touches the surface of much of the subject, as it's a pretty deep thing to talk about. Okay, so just a little bit about who we are as Multipix Imaging. We have been a distributor of machine vision products for over 20 years. We have a lot of experience in the subject in that time and have represented many different manufacturers. We exist really to help customers with vision projects right the way through the design cycle. So that means right from the sort of concept with recommendations for the right products, through prototyping with loans and assistance that way, right to the end run, providing the products and supporting in post support anything that might come up. We very much have a proactive way of doing that. We run little seminars, what we call Wise Up events, and we really sort of put out as much information and do the sale in a way that is like a tutorial style rather than pure sales. Okay, so a little bit now onto the presentation that what we're talking about today. This is a general definition of what we're talking about, which is anomaly detection, more specifically in this case novelty detection. And it is the process of looking for, identifying unexpected, it says items, but unexpected defects generally, when we're talking about what we do in data sets, so that, in other words, things that differ from what is a good sample. So anomalies are outliers from the norm, and there are two basic assumptions, as it says here. One is that the anomalies occur rarely in the data, and the second assumption is that they do actually differ significantly from what you expect. So they're relatively straightforward to pick up. So but it is developing. It's developing a lot as algorithms are getting more sophisticated. Okay, now these anomalies are, because they happen fairly infrequently, they are quite difficult to define, and in fact maybe they're impossible to define, because we may never have seen the defect before. In other words, it may be something like a smudge on a product or a crack in something that actually is very difficult to define, and therefore we actually want to define what we are looking for as a good product, and anything that differs from that we want to pick that up. So that is, it actually makes it very difficult, and training for this, the training set that we provide, requires a completely different approach to any conventional algorithms that you may have used for vision projects in the past, so-called deep learning. Okay, so what is deep learning? As it says here, deep learning is a form of neural network, but it has a hidden computational layer. That means you can expand training sets massively. We've actually, into tens of thousands of examples in your training sets if necessary. And what it means is, you can expand it, as it says here, pretty much infinitely in a deep learning algorithm, rather than, with a neural network, it has limitations to how many examples you could give. And as it says here in the second paragraph, the more data in the training set, the better the performance. But of course, the drawback is the more data you have, the more computational power is required. I quite often find that with deep learning classifiers, they have need to have extremely powerful PCs or host machines that process these things. It could take days or even weeks to process the sheer volume of data. So that's really the drawback of deep learning, but it's hugely powerful. Okay, so a little bit more deeper into deep learning. There are three different implementations. Most deep learning algorithms have these three. In this case, we're talking about a product that's just on the left there from a company called MVTech, called Halcon. They have these three implementations. One is classification, so distinguishing different types of objects that may have lots of variation in them. The second part is detection of one type, and then the third one is segmentation, and this is what we're going to be talking about today. So anomaly detection comes into the segmentation implementation. So this is what we'll look at during the presentation. So now, it seems that there are all sorts of different options all the way through this, but segmentation has two different ways of going about it. The first way is so-called supervised segmentation. Now, this is where we are looking for specific types of defect, and we would need to give examples of each of those defects in our training set. So it is possible to segment anything, as it says here. So it could be different objects, it could be different types of defect, but they would need to be defined. So again, for this anomaly detection, it's not suitable. The unsupervised defect segmentation, this is where the key is. So this is when we only train with good images, and it's possible to look for things that are different from our standard model, what we call, or our golden template, sometimes referred to. So, sort of extending that a little bit more about, going back to the supervised one, just to give you an example, really. If we were looking at in this case, we've got hazelnuts here. Now, of course, it's an organic product which has a lot of variation from nut to nut. So, a rejection class looking for defects in these things, such as cracks specifically, and defining what they look like, is very, very difficult, if impossible, in fact. And therefore, it's a good example of something that we could not use supervised segmentation for. If we were looking for defects in this type of product, it would have to be unsupervised. In other words, we give it lots and lots of examples of what good nuts look like. Each one is different, but we've got many, many examples of good examples. And therefore, we're looking for something that differs from that, such as cracks or holes or whatever defects they are. Okay, back again to unsupervised segmentation. The advantages of this classification are that we get two outcomes. Either we have a good outcome or we have a defective outcome. In other words, not good. The defects in the image are highlighted, so it shows us which pixels it thinks are not what they should be. So it can detect things that we've never seen before, as I mentioned previously. So unforeseen defects can be found. It uses the power of deep learning, as we've just said, but it's very simple to use. Because now it says here we can work with very few images, maybe as few as 10. The reason for this is depends on the nature of what we're looking at. If what we're looking at varies very, very little, in other words, it's not an organic product, maybe something that is very, very regular, and from one sample to the next there is very few or very subtle differences, then we need very few trained images to define everything we think that is good. And the great news about that is if you haven't got many trained images, then the speed is incredibly quick. So that they are very, very good advantages. The disadvantages are that, of course, because you are looking for things that you have not actually specified, it's not as accurate or dependable in classification as a supervised segmentation would be, because you haven't defined what you're looking for. So you will certainly not be up in the 99.9% that you might be with other ways of looking for segmentation, but you can look for things that you don't know what you're looking for. So it doesn't work well with some types of defects. In other words, very small things that may be difficult for it to distinguish, or defects that are very smooth or smooth things out. So there are a few disadvantages. Okay, a little bit more on the training. So as we've already mentioned, the training set contains only good samples. The deep learning network therefore has no specific defects, and it will detect anything, which is anything other than good. It means that no pixel precise labeling or definition is required. Now that's a key thing. So of course, a lot of the time when we do training sets for deep learning, if there are any errors in a labeling, in other words, telling or putting those defects into the right classes, then of course then there's a serious problem. So the fact we don't have to actually label our training set is a big advantage. Okay. So, as I've said previously here, if there's very little variation from sample to sample, then very few examples are needed in a training set. So, training sets, even for organic products, don't really contain anywhere near as many examples as you might think you'd need in a full deep learning classifier. This is because we're not starting from scratch. This anomaly detection is done with underlying samples that have been trained in the by the guys that developed the algorithm. So we're kind of using something on top. It's a second layer on top of that, the things that are underneath. It means that because we need far less computational power, we can even train on a CPU. When I mentioned previously, mainframes were required and may take days or many days to actually do the number crunching. Well, because we've got very few samples, this can be done very quickly on a CPU. Okay. So quick summary. So we've got very few training images, only good ones, no labeling, and training on a CPU. So let's get to an example here. We have a bottle here that we're looking down on from in plan view, and this is giving us some example numbers that might apply to this kind of training. So with well-aligned objects, there's even less complexity if we get the bottle in the right place. We don't actually need very high resolution images either. So in this case, there's very little going on here, so we can use pretty low resolution images. 320 by 320 pixels in this case is what was used. Only 20 training images were used. It took 6 minutes for us to do the training on an Intel i7. And then if we sort of look at the inference of that on what would take on a GPU, it would have only taken 30 milliseconds. So that's great. I hope you've got better glasses than I have. This is a few numbers showing us really the differences between what we would do on a CPU versus GPU. So you're very welcome to stop this pause on this slide and have a look at the time differences. You can see it's several orders of magnitude. Once we get up into higher res images, you have 79 milliseconds here in unsupervised versus what is that? 2 seconds, 2,000 milliseconds there. So huge differences. So now on to a few examples. So you can see, here we have examples that are quite difficult to define. And the reason for choosing these is that it'd be very, very difficult to do any kind of classification with most algorithms on these specific examples. First one being coffee beans here. We can see in the top image there that there are, your eyes pick out that there are different colours there and different forms. The coffee beans are not full, or they've been distorted in some way. With the waffle there, we've actually got some colour variation on the waffle, but I don't think it's just that we're highlighting here. Is actually it's made the texture of the waffle has also changed. And then on the right hand side, we've got a textile material, and of course it's very, very difficult to pick out any defects in very fine weave textile. So it's another great example of where this kind of algorithm can be well used. So a few more examples. We look at the top row here that's got the green boxes around it are the example, the training examples, and the ones in the center there are defects that we've picked up. And then the bottom row is actually a zoomed in version of those defects. So looking from left to right, the bottle there that we looked at a few slides ago, that has a little chip out of the top of the bottle there that you can see is picked up very readily. This is the second one in from the left is the cores in an electrical cable. We can see that there are some cores that are protruding out of the end that's been cut and actually going across onto or close to one of the other cores, which would obviously be a problem. It's almost touching. The third one along is some kind of pharmaceutical capsule, and again there's a defect there in the coating. The fourth example is a textile material. As we zoom in, you can see there's some broken weave in there. The next one across is the nut that we looked at previously with a hole in it, and then we've got a small sort of scratch or indentation in a metallic product in a nut. So it shows you there's a lot of variation in those. You can imagine for the training sets, for the sort of far left and far right, the perfect examples would vary very little. So it's likely we wouldn't need many examples. That said, the reflections on the metallic surface could vary a bit. So we would need to give quite a few examples of how much variation we could expect with those reflections. Okay. So I did say it was a pretty brief outline of trying to get your head around what this anomaly detection is all about. So these conclusions, I think, is probably a good summary of what we talked about. So if we go through again, we think that anomaly detection, as I think that the title of the presentation said, it redefines previous thinking, because we can look for things that we don't even know what we're looking for. So as it says here, it's possible to find undefined defects. Well, that in concept was never possible before the concept of anomaly detection. It's also very fast and very adaptable, which is great, and you can apply it to organic products and fixed samples. So all those things are just are really very, very good conclusions from it. But there's a big but, and this is probably the key to whether it's the right algorithm for you or not. The but is that it's just not capable of very high accuracy. There's no way we could say that it would be 100% accurate. So we're looking in the 90s generally, and so unfortunately it means that for many applications it's not quite the answer, but it could be the answer if used in combination with other algorithms. So if we're looking for specific defects first of all, and there are no specific defects, this could be used as kind of the end run, and it would maybe pick up 95% of any undefined defects, in which case, if you put all that together, we could be up in the very high 90s, which might be acceptable. But I think it's very, very worth, this slide is a very important one. So there's a few the video links that are very useful. Please scribble these down and have a look at them. They are from two of our suppliers, manufacturers. The MVTech one that I mentioned earlier, and another couple of videos here from another supplier called PCAT. So they're very good to watch. And so that brings me on to acknowledgements. I would like to thank our suppliers for the material used in this presentation, specifically MVTech, Eurosys that also do some software, eVision, deep learning software, and PCAT, who are deep learning only. So yeah, many thanks to those guys. And that brings us to a close. So thank you very much. Hope you learned something. And by all means, contact us. Look us up on our website that's at the bottom there, multipix.com, and hopefully we can help you. Okay, thanks very much.